Okay, we're going to quickly kind of solve this problem. Again, I'm leaving the units off of these things. I don't like to do that, but let's not worry about the units right now, but be sure that you use them when you do a problem where the units are given. So the acceleration is 6i minus 8j. That's a constant acceleration. And we have the initial conditions that our initial position is 2i minus 5j, and our initial velocity is 12i plus 5j. So what does this mean? Let's just draw a picture. Here's our coordinate system. R of 0 equals 2i minus 5j means that we come out 2 units on the x and up, well, down 5 units. And we arrive at a point here. Here's our R of 0 vector. And here's our initial point. So we're starting from this point. And we're starting from an initial velocity, 12i plus 5j. Now remember, position is measured in one system of units, velocity is measured in units of, positions measured in units of length, velocity is measured in units of length divided by units of time. So that when we draw our scale for the v of 0 vector, we're not going to use the same scale. We don't have to use the same scale we use for our x and our y. So I'm just going to draw a vector. Okay, 12i, let's say that's out to here. There's 12i, and 5j, that might be up to here. And right here's our v of 0 vector. So this is our vector v of 0. And we also have this acceleration vector, which again has different units than either of the other two. It's got distance, it's got units of distance or length over time squared. And the acceleration is always the same. So let's just draw a vector indicating 6i minus 8j. Let's just draw it from right here. And then we'll just draw a bunch of them. Okay, so let's say this is 6i in units of acceleration. And here's your negative 8j. So right here is an acceleration vector. Well, presumably everywhere this projectile is going to go, or this, it might not even be a projectile, it might be a completely different situation. This object is going to go. It's going to start from here with this velocity. It's going to have this acceleration everywhere. So we could permeate the plane with acceleration vectors. I don't want to mess up my meticulous labeling over here, so I'm not going to draw them in here, but we can understand now if we start with a velocity v0 in this direction from this point, what's our trajectory going to look like? Well, these acceleration vectors are always going to be bending the path of the object toward themselves. So that the object is going to, right now the acceleration is going to be in this direction, means the change of velocity will be in this direction. So this is going to start curving, maybe fast, maybe slow, because again, there's no indication of exactly what our scale is here. Maybe something like this. Okay, it's going to immediately diverge from the initial velocity vector and continue to diverge faster and faster. That's not particularly well drawn. I was influenced by my labeling and a lot of other things, but hopefully you get the idea. Now let's just see how this works out. I think it's safe to remove our lighthouse. Had to put the lighthouse up safely. So how do we do this? Well, v is going to be the integral of a of t dt. And it's clear that if we integrate 6i minus 8j, we get 6t plus a constant times I plus negative 8t plus another constant times j. Now, what's the constant here and here? Well, let's just go ahead and call these constants C1 and C2. And you might well see where this is heading already, but if not, stay with us. Okay, so V is this, and what do we know about our velocity vector? We know that V of 0 is 2I minus 5j. And of course, V of t equals this, so that V of 0 has to equal C1I plus C2j, so that C1 equals 2, here I was looking for it, and C2 equals negative 5. And our velocity function, V of t, make sure we're visible here, yeah, it's good, equals 6t plus 2I plus the quantity 8t, well, it's going to be plus a negative 5, I'll just write that as negative 5, times j. So we've got our velocity function. How do we get our position function? Well, we're going to integrate the velocity function, and we're going to substitute, and we're going to set that equal to our position function. You know, I must have been too close to the board because this is supposed to be 12, and this is supposed to be plus 5. I guess I'd better change that, or it's going to get really, this is 12, this is plus 5, so I'll make this plus 5, and that'll make this 2 at 12. Kind of getting, I don't know whether it's worse to have that smudge there, or let the plus sign and the 1 run together. Okay, so there's our velocity function. I think you should understand pretty easily that I corrected that, and the correction's pretty straightforward. Okay, now R of t is integral of your V of t function, which is integral of 6t plus 12I really kind of need to write that dt. Then I'm going to have a really bad looking equal sign there. But we can have that on there. Okay. And then at plus 5j and there's our dt. Just got it in before we ran out of space on the edge of the board. And everything going downhill here. We'll try to straighten that out. Okay, well, that's a very straightforward integral. And we're going to get 6t plus 12. I'm going to use C1 again for my constant because the C1 that I used for my constant here has already been evaluated and it's gone now. So we're going to use a different C1 here. We're going to have 8t. What am I doing? I'm going to pause here for a second and correct that. Okay. Started writing things down without even thinking. When we integrate 6t, of course, we're going to get 3t squared. We integrate 12, we're going to get 12t. And our C1 is, again, as I explained, not the same as the C1 we got here. We've already evaluated that, so it's kind of wiped off the slate. So we're going to use C1 again, just to avoid symbol proliferation. We integrate the 5, we get 5t. That'll be plus C2 times j. And then we apply our initial condition. R of 0 equals 2I minus 5J. So, well, 3t squared plus 12t plus C1, when t equals 0, I'll write it out, 3 times 0 squared plus 12 times 0 plus C1 has to equal 2, so that C1 equals 2. And a similar step over here tells us that, I can write that, 4 times 0 squared plus 5 times 0 plus C2 has to equal -5, so that C2 equals -5. And our final function is R of t equals, what, 3t squared plus 12t plus 2I plus 4t squared plus 5t minus 5j. That is very straightforward. Once we've evaluated C1 and C2, we just write this out, substituting the 2 for C1 and the -5 for C2. So this is going to be our position vector. Plug in the time, we get the position. Now again, I didn't write units on these quantities in interest of time and so forth, but be sure that if you have a situation where units are involved, that you do write the units. Now this comment, uniform acceleration in the I direction gives us a quadratic position function for the I direction. Uniform acceleration for the J direction gives us a quadratic position function for the J direction. Not every situation you encounter in the problem sets or in the course is going to have a uniform acceleration. And you can easily make, could call that 6ti minus 8t squared j and see what the integrals do, see what your function ends up looking like. Your R of t would end up being a cubic function, your j would end up being a fourth degree polynomial, a quartic. And of course, you could parameterize this curve, express it as a function of x or as a function of y, and get the y versus x function that defines this curve. But that would be a lot of work, and usually this parametric representation is going to have its advantages.